Hello everyone. Today I will be demonstrating a web-based virtual lab for pulse code modulation or PCM. PCM is a fundamental technique used to convert continuous analog signals into digital format. The core process involves three main steps. First, the analog signal passes through a low-pass filter to prevent aliasing. Next, a sampler creates discrete time intervals. Then, a quantizer maps those amplitudes to discrete levels. And finally, an encoder converts a level into binary code for transmission. Before starting, users can read the step-by-step procedure and take a quick multiple choice pre-test to assess their foundational knowledge. Moving to simulation, we designed an interactive dashboard. Users can precisely adjust message amplitude and frequencies. For both the message and sampling frequencies, you can toggle between Hertz and kilohertz. We can also select the signal types. It has sine, cosine and random. For quantization levels, we support a wide range from 4 all the way up to 256 levels. And you can choose either binary or gray encoding schemes. Before simulating, we must remember the Nyquist-Shannon sampling theorem. To recover a signal without distortion, the sampling frequency must be at least twice the message frequency. Otherwise, aliasing occurs. Let's start by purposely breaking this rule. I will set the amplitude to 5 volts and the message frequency to 50 Hz. The Nyquist theorem requires a sampling rate of at least 100 Hz, but I am going to set the sampling frequency to just 90 Hz. When we simulate, the sampling analysis box below clearly shows a warning. The ratio is 1:8, which is less than 2, indicating that aliasing will occur. If transmitted, this signal would be completely distorted. Now let's fix this. I will increase the sampling frequency to 400 Hz. The analysis box now turns green. Let's look at channel 1, the transmitter. Here is our original 50 Hz input sine wave. The sample graph shows the discrete snapshots taken 400 times a second. Next is the quantized signal. Notice the staircase effect. Since we selected 8 quantization levels, the infinite analog values snap to the nearest of 8 horizontal lines. The gap between the original wave and this step is called quantization noise. Finally, the encoded signal converts these steps into a binary pulse stream ready for the channel. To reduce the staircase error, I am going to increase the quantization levels. In the quantized graph, the samples are now so dense that the staircase effect is barely visible. It accurately traces the original analog wave, which demonstrates how high quality audio files work. Finally, let's retrieve our message. At the receiver, we first decode the binary data, returning it to its quantized steps. Then we pass it through a reconstruction filter. The result is a smooth sine wave that perfectly matches our input phase and frequency. After simulating, users can take the post test to verify their understanding. and they can view the result tab for a summary of the experiment's key insights. This concludes the demonstration of our PCM virtual lab. Thank you.